Hi everyone. The paper I'll present is Markets with Heterogeneous Agents, Dynamics and Survival of Bayesian versus No-Regret Learners. This is a joint work with David Easley and Eva Tardosh. In this paper, we study markets in which users use learning algorithms and how different approaches to learning interact and compete. And this is motivated by a transition in many markets and platforms towards using learning-based algorithmic agents. We see this in stock exchanges, online auctions, and many other settings. And the basic setup we'll have for a market with learning agents is that we have some set of market participants or users. There is some set of assets in which the users can choose to invest. And the users are going to use learning algorithms that will make investment decisions on behalf of the users. And so there is some repeated interaction in which the agents make those repeated or recurrent investment decisions, and those decisions lead to some outcomes in the market, and those outcomes are translated back to the user's eventual wealth. And a question that a user can ask themselves here is, what kind of agent should I use? What kind of algorithm should I use? Especially given the fact that the other users competing with me are also using learning algorithms. So which types of agents should users choose to use? And what learning approach performs better in this kind of a competitive setting? And we compare two different theories for learning. Both have been studied a lot in this context of portfolio optimization, Bayesian learning, and no-regret learning. And they've been studied quite separately in economics and computer science. And the questions we ask are first, which approach performs better if we let Bayesians and no-regret learners compete in the same market? So which approach to learning performs better and in what conditions? And also, what is even the meaning of regret in this kind of a competitive market? What's the relation between regret and long-term survival? And if I have low regret, say I have log T regret, does this imply that I'll be successful in the market, that I'll have a high wealth level? And it turns out that the answer for the last question is negative. At least it can be negative. You can have very low regret, like log T, but also have vanishing wealth in the market. So our plan would be to first look at the market model. We use a standard model of our securities for these markets. Then we'll say a few words about no regret and Bayesian learning and what we know about them in this context. Then we'll see our first result about the relation between regret and survival in those markets and how we can use regret to compare between different types of learners. Then we'll talk about the regret of Bayesian learners. We'll find that Bayesian learners have very low regret in this market. And actually, Bayesian learners, when Bayesian learning is done correctly, are able to drive out of the market no regret learners. But on the other hand, we also find that Bayesian learning is very sensitive, very fragile, and no regret learning is more robust in this sense. And then we'll see a very simple adaptation of the Bayesian update rule that improves robustness, at least for some settings of distribution shifts. And then we'll summarize. Okay, so in our model, we're going to have n agents. Each has some initial wealth level. And there is some set of assets. And we're going to use the arrow securities model, in which every asset is identified with a single state. And in every round, only a single state realizes, and only the asset associated with this state pays off. The other assets do not pay off at this step. And this model is actually more general than it may sound. Every complete market can be described by some set of arrow securities. And we're going to assume that there is some stochastic process. The states are going to be IID from some data generating distribution Q. And in every step of the dynamic, agents make investment decisions. And the decision of an agent indexed by n is alpha n st. It's the fraction of agent n's wealth at time t invested in asset S. And then some state is realized, there is some payoff, and the payoff is split between the investors. And the learning agents we're going to look at are trying to optimize the growth rate of the wealth, or the log of wealth objective, which is a commonly studied objective in this context of portfolio optimization. And no regret learning approach here, the learners directly respond to the changes that they experience in their wealth levels. And we know about methods that guarantee very low regret in this context for the log of wealth objective. We can get a log T worst case regret, which is much lower than the standard worst case regret of square root T that we used to see. Importantly, no-regret learners do not rely on a prior. In fact, those methods are actually able to consider the entire simplex of possible investment profiles as valid strategies that they can learn. The Bayesian learning approach is very different. So here, the learners do not directly respond to the changes they experience in the wealth. Instead, they observe the stochastic process and try to learn what the stochastic process is. And in every step, they best reply to their current belief about what the stochastic process is. And the best response for an agent is to actually bid its beliefs. So this means to invest a fraction in every asset that is equal to the belief that this asset pays off. And specifically, if some agent happens to know the data generating distribution Q, then it is optimal to invest according to Q. And we know from previous results that Bayesian learners who have a finite prior survive against an investor who uses Q as the strategy. And this is something we know. And importantly, Bayesian learners rely on a prior. So there's going to be some set capital theta of models that the Bayesian considers as possible data generating distributions. And we're going to focus on finite priors in this talk. So first result shows a relation between the notion of regret and long-term survival in the market. And we see that there is a very clean characterization of this relation. We find that an agent survives if and only if its regret difference compared to any other competitor in the market is bounded by a constant at all times. And on the negative side, if this regret gap diverges at any rate compared to any other competitor, then this agent vanishes from the market. Implications are first, low regret is not enough. The agent must have the best regret rate in the market to even survive. And second, even constants in the regret rate do matter. For example, if we have an agent that has log T regret and a different agent that has log T over 2 regret, the first agent is going to vanish from the market. We still have log T regret, but also zero wealth. And to understand this, we need to look at the wealth levels of the agents, or alternatively, we can look at the wealth ratios. So RNMT is going to denote the ratio of wealth levels between agents N and agent M at time T. We're going to focus on wealth ratios for two reasons. First, wealth ratios are enough for us to understand which agent survives and which not. And second, when you analyze wealth ratios, the prices in the market cancel, and the dynamic of wealth ratios depends only on the investment strategies and the stochastic process. And it simplifies the analysis. And specifically, we're going to look at the log of wealth ratio, which will be more useful for our case. And when we look at the log of wealth ratio, so if it remains finite at all times or diverges to positive infinity as time goes on, this means that agent N survives. And if in the limit as time goes on diverges to negative infinity, it means that the agent vanishes. And to see the proof, we're going to first write down the utility for an agent given a sequence of investment strategies alpha 1 to alpha capital T, which is going to be simply the log of the eventual wealth at time T given the sequence of strategies that was played. Then we're going to write the regret of the agent in the usual way. It's going to be the utility of the best fixed strategy in hindsight, minus the actual utility that was obtained with the strategies that were played. And then using our expression for the log of wealth ratio, we're going to get this expression, which basically tells us that there is a very simple relation between regret and wealth. We see that the wealth ratio or the log of wealth ratio between two agents plus some constant equals the regret difference. And this gives us the result. Okay, so we know that only the learners who have the best regret rate in the market survive, and we know to say something about the regret rates of no-regret learners. And now we want to say something about the regret of Bayesian learners. And we find that Bayesian learners actually have very low regret. Bayesian learners who have a finite prior that allows for learning the correct distribution Q actually have constant regret that does not increase with time. And therefore, in competition with Bayesian learners, only other learners who also have constant regret survive. And the idea for proving this is first to use the known result that I already mentioned, that a Bayesian learner survives against a competitor who uses Q as the strategy in every step. Second, in a different theorem that I skipped here, showed that we can actually calculate the regret level of such an investor who uses Q in every step, and we find that this regret level is constant. And finally, we combine those two facts with our previous theorem and get that if a Bayesian learner survives against a player using Q has constant regret, and survival implies that the regret gap is constant, then Bayesian learners must have constant regret as well. So that's the idea. So just to recap, we know that only the learners with the best regret rate survive. And we know that Bayesian learners have a very low regret level. So they drive out of the market any other learner who has regret that increases with time. But on the other hand, we find that Bayesian learning is very sensitive and very fragile under small errors or noise. Bayesian learners who have a finite prior that does not include Q in the support, can include something very close to Q but not exactly, actually have linear regret. And also Bayesians who do have Q, the data generating distribution in the support, but make small errors with zero mean errors in every step in the update process also can have linear regret. So we see that Bayesian learners have very low regret, but if we add very small mistakes, the regret jumps immediately from being constant to being linear in time. And we can demonstrate this first result here with an example. So let's say that we have some Bayesian learner who has something close to the true distribution in the support, but not exactly, with some epsilon error. And for the example, we'll have two states. The true distribution Q is going to be probability 0.76 to state A. And the support of the Bayesian's prior is going to be multiples of 0.1. So you see that 0.76 is not exactly there. And for the example, we'll start with a uniform prior. And this is the kind of dynamic that we get for the belief about the probability of state A. So we start from the uniform prior, but very quickly the belief converges to 0.8, which is the closest distribution within the support to the true distribution 0.76. Because we converge to something that is not exactly right, and after some finite time t, and this time is finite because the convergence rate for Bayesian is exponential, the belief is going to be bounded away from Q. Then we start accumulating constant regret per step, so linear regret overall. Notice also that during this dynamic, the Bayesian learner actually does play convex combinations of the prior, and at some point, he also plays the correct distribution Q and gets high payoff when he plays this distribution, but the belief continues drifting away to 0.8, which is in the support because the Bayesian does not respond directly to the payoffs. And here, we'd like to switch to looking at some kind of a best of both worlds result because we saw that Bayesian learners are very efficient in learning when it's done perfectly, but very sensitive. No-regret learning is more robust. And here we're going to show a very simple adaptation of the Bayesian update rule that improves robustness, at least for some scenario of distribution shifts. So the actual data generating distribution can change now over time. For no-regret learning, we know that there are adaptive methods that actually can give us low regret under distribution shifts. If there are k shifts in t steps, we can get k log t regret compared to the benchmark of actually knowing in advance when these distribution shifts are going to happen and which shifts these are. But we also know for no-regret learning that typically regret increases with time also when there are no distribution shifts. Or for Bayesian learning, we can get constant regret if there are no shifts, but we show that a Bayesian learner that is not aware of the distribution shifts actually performs very poorly under distribution shifts, even if the shifts are only among distributions that are within the Bayesian learner's support, and even if there is only a single distribution shift, the regret can still be linear in time. And this is essentially because the Bayesian learner converges very strongly and very quickly to the first distribution it observes. And after a distribution shift, it takes a long time to forget what the Bayesian has learned and converged to, and to recover from this, which leads to linear regret. And the idea for the method we propose is to add a very simple adaptation to the Bayesian update rule. So the learner is going to do something very similar to a standard Bayesian learner. In every step, it's going to actually invest according to the current belief, just like a Bayesian, and then observe the realization of state and do the standard Bayesian update, just as usual. And the difference is that we add, after this Bayesian update, a small regularization to the beliefs and renormalize the beliefs. The regularization decreases over time. And we showed that this very simple adaptation gives us this kind of a best of both worlds result, where if we have k distribution shifts in t steps, we can get k log t regret. So we're competitive with those adaptive no regret methods. But if there are no shifts, we can still get constant regret, just like a standard Bayesian. So we can actually get both. And the idea for this is that when we add this regularization, then when the weight on some incorrect model is large during the learning process, then the regularization has very little impact and the convergence rate is still exponential. But when the weight on an incorrect model becomes small or comparable to the level of regularization that we add in every step, then, of course, convergence rate is no longer exponential because we add this amount of noise in every step. But we also showed that the contribution to the regret at this point is also very small. And the observation is that this exponential convergence rate that Bayesian learners do have was sufficient for getting constant regret, but it's not a necessary condition, and we can still get constant regret also with this regularization. Okay, so to summarize, to recap, we talked about regret, competition, and survival. We saw that in competition, low regret is not enough. We need to compare regret rates between different learners who compete in the market, and only the learners with the best regret rate survive. And about Bayesian versus no regret learners, we saw that perfect Bayesians have a constant regret, and they're able to drive out of the market any other learner who has regret that increases with time. But on the other hand, Bayesian learning is very fragile, very sensitive to small errors. And in this sense, no regret learning is more robust. And about the robust Bayesian updates, so that by adding a simple regularization, we get a kind of a best of both worlds result where we get constant regret without distribution shifts, logarithmic regret with shifts. And with this, I would like to take a step back and go back to our first slide and look at the bigger picture, where in this paper we had a scenario where we had a market where users use learning agents and how different learning approaches interact and compete. And I think this is a part of a broader context in which in many settings we see now that more and more learning agents and AI agents are being deployed, and those dynamics between the agents raise interesting questions and an interesting set of questions about how they impact the markets, how they impact the incentives for the users, how should we design those kinds of markets, and various other questions. I think this is a very interesting and exciting time to be exploring those kinds of settings and questions. And with that, I'll thank you all for listening.